Welcome to the University of Kentucky's Backyard Streams program. During this webinar, we will explore the factors that cause streambank erosion, explain the streambank characteristics most easily managed by homeowners, and we'll discuss methods for stabilizing streambanks. Streambank erosion refers to the removal of soil and other material, such as rocks and vegetation, from the streambank. Streambank erosion is a naturally occurring process, but the rate at which it occurs is often increased by anthropogenic activities such as urbanization and agriculture. Changes in land use can cause streambanks to erode at rates much faster than those seen in natural systems. Sediment is one of the largest pollutants to our nation's streams and rivers. The sediment found in streams and rivers comes from two main sources: the watershed, and the streambanks. Depending on the location, the amount of streambank erosion can be quite substantial. Studies have reported rates as high as 92% and as low as 17%. Research by the United States Department of Agriculture's Agricultural Research Service shows that streambank erosion is the main cause for the high suspended sediment levels found in tributaries to the Mississippi River. Waters with high suspended sediment loads not only impact the morphology of streams, but they also negatively impact aquatic life. High levels of suspended sediments can abrade the gills of fish and make it difficult for fish and predators to find food. Suspended sediment can also act as a carrier for sediment-bound pollutants, meaning that when sediments are introduced to streams, other pollutants, such as phosphorus or heavy metals, may be introduced into the water as well. In some cases, these pollutants may be more harmful than the sediment itself. Knowing that excessive streambank erosion is such a large contributor to the stream's suspended sediment load is motivation for understanding why streambanks erode and developing methods to reduce streambank erosion to more natural levels. Remember, all streams experience erosion and deposition. The important point is that such erosion and deposition is not excessive or significantly greater than that of the undisturbed system. Streambank erosion is problematic for a number of reasons. When streambanks erode, valuable land such as crop or livestock fields are lost. Critical infrastructure, such as bridges, roads, and underground utilities, may be exposed and damaged. Eroding streambanks can be a safety concern for humans, livestock, and wildlife, as overhanging banks can collapse. The addition of sediment to streams reduces water quality by increasing suspended sediment concentrations. Aquatic habitat quality is reduced due to embeddedness or the filling in of pore spaces by sediment. Streambank erosion is driven by hydraulic and gravitational forces and is dependent on the characteristics of the banks. Hydraulic forces are those associated with the movement of water, particularly the velocity and direction of water flow. A hydraulic failure occurs when water from the stream causes material to detach from the bank. The photo on the left shows eroded streambanks due to hydraulic forces. A geotechnical failure is a mass failure that occurs when gravitational forces exceed the bank's ability to resist said forces. Examples of such failures are the collapse of an overhanging bank due to gravity, such as in the photo on the right, or bank sloughing. Such failures are often related to soil moisture. When soil is wet, its ability to withstand stresses decreases. Commonly, streambank erosion is a combination of hydraulic and gravitational forces. Before proceeding further, it is important to understand one of the main hydraulic forces causing streambank erosion. When and how sediment particles move depends largely on their size, density, shape, and whether they are cohesive and stick together, such as clay, or non-cohesive, such as sand. One reason particles move is shear stress. Shear stress, or tau, is the force exerted by the fluid or water on the boundary being the stream's bed and banks. It is defined as the product of the specific weight of water, gamma, hydraulic radius, which is often approximated by depth or d for wide streams, and slope or s. The shear stress equation states how slope and or depth increase, the ability of the water to move sediment also increases. Understanding the factors that control shear stress is critical to understanding why streams erode. 8 stream characteristics influence stream bank erosion rates: bank height, rooting depth, root density, bank angle, surface protection, bank material, and stratification. These variables are part of the Bank Erosion Hazard Index, or BHI model, developed by David Rosgen. Understanding the effect of each of these variables on stream bank erosion is important for stream assessment and restoration. The first variable to assess is the bank height. This variable is focused on the question of whether a stream can access its floodplain. For a stream that is incised, meaning the top of the bank is greater than bank full, the stream will not easily access its floodplain. In such cases, stream depth will continue to increase, causing shear stress to increase, thus resulting in excessive stream bank erosion. For streams that are not incised, meaning the top of the bank occurs at bank full, shear stress does not become excessive, and thus stream bank erosion does not become excessive. These photos show streams in which bank full and the top of the banks coincide. Such streams have low shear stress and low rates of erosion because floodwaters can easily access the floodplain. Contrast the previous photos of stable streams with these photos of incised channels. For both streams, bankful elevation is much lower than the tops of the stream banks. As a result, the streams experience high levels of shear stress because the waters become quite deep before they can access the floodplain. These high levels of shear stress result in excessive stream bank erosion. For the photos on the bottom left, stream bank erosion is active and ongoing. For the photo in the top right, stream bank erosion is occurring at a slower rate. For most places, the stream has formed a new, albeit more narrow, floodplain at a lower elevation, as denoted by the green arrow. This floodplain provides some relief. However, note that the stream bank erosion that is occurring where the stream does not have access even to a small floodplain. The location of high erosion is denoted by the red arrow. Rooting depth is the second variable that requires assessment. The question to ask is, how deep are the roots compared to the height of the bank? Roots are extremely effective at holding the soil in place. However, the effectiveness of roots is limited to the extent of the stream bank that they span. Roots that are deep and span the entire height of the bank are very effective. Roots that span only a portion of the bank height are limited in their effectiveness. For instance, where the predominant root depth or mass does not extend the full length of the bank, the stream banks can become undercut and can lead to bank collapse. Tree roots, for instance, can extend to a depth of a few feet. Grasses, which are common along stream banks in many urban and agricultural areas, often have root systems that extend less than 1 foot. It is important to remember that when assessing root depth, consider the depth of the majority of the roots. These photos show stable sites where rooting depth is quite deep. The stream banks are aligned with trees whose roots extend the full length of the banks. In contrast, these photos show shallow rooting depths. The vegetation along the stream banks consists of grasses whose effective rooting depths are typically 1 foot or less. In the case of the top right photo, it is even less likely. Such shallow rooting depths mean the stream bank is left unprotected from the shearing force of higher flows. The third variable to consider is rooting density. When root density is low, the soil is held weakly in place as there are few roots. The hair on a newborn baby is a good example. Because the hair is often thin or not dense, heat can readily escape from the baby's scalp. When stream banks have few roots holding the soil in place, soil particles can easily detach. When root density is high, the soil is held tightly in place. For optimal stream bank protection, the goal is to use vegetation with deep, dense root systems. These photos show examples of riparian vegetation whose dense roots are providing substantial protection from stream bank erosion. These photos, on the other hand, show the ineffectiveness of a few roots at preventing stream bank erosion. Bank angle is the fourth variable to assess. Bank angle is measured to determine the potential for the stream bank to experience geotechnical failure due to gravitational forces. Streams that are less vertical and have more relaxed slopes are less likely to erode. Streams that are vertical or overhanging are more likely to experience mass erosion by geotechnical failure. These photos show examples of streams with low or relaxed bank angles. When bank angles are low, floodwaters can spread out over a greater area. As volume is the product of area and depth, a larger area means the increase in depth is smaller for the same volume or discharge. By keeping water depths low, shear stress is also lowered. This photo shows a vertical bank. The stream cannot access its floodplain, so floodwaters are contained within the channel. Increases in discharge or volume are not spread out over a larger area, so depth increases rapidly. Large increases in depth result in large increases in shear stress and hence the ability for water to erode. The fifth variable to consider is surface protection. Surface protection refers to the percentage of the stream bank that is protected from erosive forces. Think of surface protection as a shield. It helps shield the stream bank from the forces exerted by moving water. Surface protection can include items such as rocks, roots, grass, concrete, or even hard engineering structures such as riprap. These photos show high levels of surface protection. In the photo on the top right, the extensive root system of a tree is protecting the stream bank. In the photo on the bottom left, gabion baskets are providing protection for the stream bank. Contrast the previous photos with these where surface protection is quite low. Even vegetation, which can offer surface protection, is largely absent. The sixth variable to consider is bank material. The more erodible the soil, meaning the smaller and less cohesive it is, the greater the potential for the stream bank to erode. Banks that are comprised of sand and/or gravels will erode more easily. Bedrock and cobble banks erode very little because the material is difficult to move. Clay soils are cohesive, meaning the clay particles stick together and are less susceptible to erosion. The seventh and final variable deals with the stratification or layering of the soil material. The more stratified or layered the stream bank material, the more easily erodible it is. Layering creates weak zones that are prone to geotechnical and hydraulic failures. Some stream bank characteristics are more easily managed by the homeowner, while others require more consideration. The type and amount of riparian vegetation will impact the variables in red: rooting density, rooting depth, and surface protection. Choosing plants with thick, deep roots can significantly reduce the amount of erosion a stream bank experiences. A caveat is the effectiveness of riparian vegetation will decrease as stream banks become taller and steeper. When choosing a restoration plan, keep this relationship in mind. For tall, steep banks, the most effective method of reducing stream bank erosion is to create floodplain access. The variables in green, bank height and bank angle, must be reduced. For such situations, it is important that the homeowner consult a qualified professional. Lastly, the variables in orange are not realistically modified. The stream will still flow through the same soils. A variety of options are available for stabilizing stream banks. In addition to creating floodplain access and planting riparian vegetation, other options include soil bioengineering, hard engineering, and in-stream structures. Soil bioengineering is the practice of using living and non-living plant material to stabilize stream banks. Examples of soil bioengineering include live fascines, brush layers, and live stakes. Hard engineering involves the use of rock, concrete, or metal to stabilize stream banks. Examples of hard engineering include riprap and gabion baskets. In-stream structures help reduce stream bank erosion by directing flowing water away from stream banks and towards the center of the channel. Examples of in-stream structures include cross veins, as seen in the photo, and J-hooks. Thank you for completing this webinar on stream bank erosion. To learn more about stream bank erosion, check out the publications and additional information sections. Also visit www.uky.edu/BAE/backyardstreams.